All right, welcome everybody. In this video, I want to discuss equilibrium and stability of equilibrium to systems of differential equations. So the system that we are going to look at in this video that we've been working with in class is a system of differential equations for two interacting populations. R is representing a population of rabbits. Maybe we're measuring these in hundreds of rabbits. F is a population of foxes that maybe we're measuring in tens of foxes. T is measuring these two populations over time. So we have two dependent variables, R and F, one independent variable, time. And so these two populations, rabbits and foxes, are interacting. This is a predator-prey model. In class so far, we've discussed what does it mean to have an equilibrium for such a system of differential equations. And in these systems of differential equations, an equilibrium would be a solution for which both the rabbit population and the fox population both remain constant. So in other words, both dr dt and df dt are both equal to zero since both of those populations don't change. So we solved and identified that there are two such equilibrium to this system, one of which is if we initially start with zero rabbits and zero foxes, that intuitively should make some sense that as time goes on, we would continue to have both zero rabbits and zero foxes. That's an equilibrium solution. And we also found this other equilibrium that we probably wouldn't be able to intuitively just identify, but there is a second equilibrium point here, namely when R is equal to 1.25. So this might mean when there are 125 rabbits and F is equal to 2.143. So when there are approximately, say, 21 foxes, this system would also be in equilibrium. So the next thing I want to discuss is whether these equilibrium would be considered stable or unstable, and what do those words even mean when we're talking about equilibrium for systems of differential equations. So we're going to create some plots below. So if you want those plots to work, we need to import a couple of packages and define our differential equation. So I want to just mention that a link to this Colab notebook is provided in the description to this video. So you can go down to the description of this video, click on the link, and start interacting with this exact notebook that you are looking at. So the first thing I want to do is just import these packages. And this is going to create a plot that's going to look at what happens if we initially start at the equilibrium 0, 0, no rabbits, no foxes. Here, we're looking at this plot in three-dimensional space with time on one axis, rabbits on this axis, and foxes on this axis. And over here, it might seem like there is some change, but what's changing here is just time. The rabbit population is fixed at 0, the fox population is fixed at 0. And if we look at this projection into the phase plane, into the rabbit-fox plane, what's really missing here is there should be a dot here at 0, 0, meaning that the solution just remains at that point. So it is not going to move at all. So the solution is remaining constant. R is equal to 0, F is equal to 0. And if we plug in the other equilibrium, which was at 1 point, R is equal to 1.25, F was 2.143, and I create a similar plot, we get a similar story just at a different point in the phase plane. So looking at this in three-dimensional space, when we vary time, we're just getting a line because the rabbit population is holding constant, the fox population is holding constant. So at some other location in the phase plane, at 1.25, 2.143, we should just have a point. This looks like it's empty here, but we have like a really small point, and both of these populations are not changing at all. So here we can kind of verify our previous result that these are two equilibrium points for this system. And so for systems of differential equations, well, what would it mean to be stable, unstable, semi-stable? Just recall when we were working with a single autonomous first order differential equation, we were using phase lines instead of phase planes to understand the long-term dynamics of those solutions. And so if we identified, say, three equilibrium for such a system, P1, P2, and P3, there are three possible behaviors. So at P3, this would be an example of an unstable equilibrium, because if we start at an initial condition really close to the equilibrium at P3, as time goes on, the solution is going to head away from that solution at P3. No matter where we are near P3, any initial condition near P3 is going to head away from P3 as time goes on. P2 would be considered a stable equilibrium, because if we adjust our initial condition just a little bit and we start close to P2, anywhere close to P2, as time goes on, those solutions would get closer and closer and closer to the equilibrium at P2. And this last equilibrium at P1, we would consider a semi-stable equilibrium, because if we start, say, just a little bit below P1 initially, as time goes on, those solutions would head back to the equilibrium at P1. However, other initial conditions that started just a little bit bigger than P1, if we let time go on at those solutions would actually not head back to P1, but they would head towards P2. So P1 would be an example of a semi-stable solution. So I want to just kind of build off of our previous knowledge and just say that the concept is the same if we're working with systems of two first-order autonomous differential equations. Now we've got a picture in the phase plane, but the idea is pretty similar. However, we'll see that the dynamics can be a little more complicated. But in the simplest sense, if I have, first of all, now our equilibrium, our coordinates, they're a pair of points. We have two dependent variables, in our case, rabbits and foxes. So each equilibrium is a point in the phase plane. And three possibilities are, well, if I start at a point close to, say, R1, F1, it's possible that for any initial condition close to this point, as time goes on, those solutions head away from that an equilibrium solution. It's possible we could be in a scenario like at an equilibrium such as at R2, F2, where if we start with an initial condition, which is close to this point, as time goes on, those solutions will head close to R2, F2. And a third possibility could be, well, here we are at R3, F3, and some initial conditions, if we start there, for example, on this line over here, if I start at an initial condition on this line, it heads back towards this, so it has some behavior of like a stable equilibrium. But there could be other initial conditions if I start on this other line, that as time goes on, we might head away from that equilibrium. That's like an unstable type of behavior. So some directions are stable, other directions are unstable. We would consider this sort of equilibrium a semi-stable equilibrium. So we'll explore these ideas in a lot more detail, and in particular, how we can identify whether an equilibrium is going to be stable, unstable, or semi-stable. For now, we've just focused on how we can identify equilibrium. And so let's take a look at what's happening with our equilibrium that we identified for our rabbit and fox model, our predator-prey model. So if I start at an initial condition near 0, 0, so let's say 0.1, 0.2, that's close to that equilibrium, I could say, what would happen in the long run to that solution, I've plotted that down below. We're getting this cyclic behavior for these populations that we saw earlier. But what I can see here is that as time goes on, those solutions are not going to head back to 0, 0. As time goes on, they're going to cycle around, but they're going to not approach. The rabbit population is not going to head to 0. The fox population is not going to head to 0. They're both going to bounce around between the rabbit population is going to go between like 0.1 and up to about 11. The fox population is going to bounce between 0.2 and up to something close to 10. So they're going to oscillate back and forth forever and not head back to this equilibrium point at 0. So this would be considered an unstable equilibrium because as time goes on, these populations are not staying close to the equilibrium at 0, 0. At the other equilibrium, 1.25, 2.143, if I start close to that point, let's say at 1.2 as the initial rabbit population and 2 as the initial fox population, and I take a look at what happens with this model, we get this cyclic behavior and we get a circle, and right in the middle of the circle essentially is my equilibrium. So it's still this cyclic behavior, but the difference here, as opposed to the previous example, is that my equilibrium is in the middle of this circle as opposed to being outside of this circle. And so in this case, the populations are oscillating again, but they're oscillating around my equilibrium. And so this is a different type of behavior that we didn't really see when we were looking at a single differential equation in the phase line. Now that we have this kind of extra dimension, the dynamics can be a little bit more complex. And we would consider behavior like this to be a stable equilibrium point because solutions that start near the equilibrium are going to remain near the equilibrium. But this is just a preview for ideas that we're going to jump into at a deeper level. But I just want to give you a preview and keep this on the back burner that the dynamics here are going to be a little bit more complex than the dynamics of a single differential equation that we saw earlier this semester. Okay, so let's take a look at how we can visualize solutions in the phase plane for a system of autonomous first-order differential equations, such as the rabbit-fox model that will be our motivating example. So we've got this same system of differential equations, and let's say we start initially with R equals 2, F equals 3. So we've got 200 rabbits and 30 foxes in our ecosystem. And what we've seen is we get this periodic behavior in rabbits and foxes, and hopefully that makes some intuitive sense why we're seeing that behavior. And so here we are in the phase plane. And one issue with the phase plane is that there is a third variable, which is time. And how can we include time in our graphs in the phase plane? So our phase plane, we can see the rabbit populations, we can see the fox populations. I can indicate where I am at time 0. I start off with 2, R equals 2, F is equal to 3. At some future point in time, about 2 years later, I could calculate what the rabbit and fox populations are going to be. But I don't know how am I moving over time. So for example, am I going from this point at t0 to t equals 2.00? Am I moving counterclockwise around this circle, or am I moving clockwise around the circle? There are 2 possible ways that I could be moving from one point to the other point. So one way that I can indicate how time in this phase plane would be to indicate an arrow that indicates how I'm moving from one point on this solution curve to another point on this solution curve. And so those directions we can get by looking at the signs of the various slopes, dr dt, df dt, and df dr. So given an initial condition at time 0, I'm at 2, 3, I can use the formulas for the differential equations to calculate the values of dr dt and df dt. So for example, down below, at t equals 0, if we know that r is equal to 2 and f is equal to 3, I can plug those values into the differential equation for dr dt and calculate dr dt is minus 2.4. It is negative. I can calculate df dt by plugging in r equals 2, f is equal to 3. That winds up being 1.8. That's a positive value. By using the chain rule, I can calculate df dr by taking the ratio of df dt and the r dt. And in this case, I'm missing an equal sign here. That would give me minus 0.75. And that just comes from taking the 1.8 and dividing by the minus 2.4. And I can do the same calculations at 2.07, and I get slopes, I get values for dr dt, df dt, and df dr that I've entered into this table below. And so let's see how we can interpret these values and use them to indicate a flow, a direction of motion in the phase plane. So at time 0, we got that dr dt was minus 2.4. So dr dt, r is on our horizontal axis. So this is measuring what direction are we moving horizontally. If that is negative, that means we're moving to the left. We're moving in the negative r direction. At this same point in time, the f dt was positive 1.8. F is the variable that we're plotting on the vertical axis. So this tells me vertically I'm moving in the positive direction. So I'm moving up. So at time 0, when I'm at the point 2, 3, this is telling me I'm moving up and to the left. So at t equals 0, we're at this point over here. Since df dt was positive, we know we're moving up. And since dr dt was negative, we knew we were moving to the left. So this vector that I'm drawing should be tangent to the curve. Just like in slope fields, those slope vectors that we drew, they were always tangent to the solution curves. And now I know exactly which direction it can go because this tangent vector could also be pointing down and to the right. But the individual signs of dr dt and df dt tell me that, in fact, I'm going to pick the tangent vector, which is going up and to the left. And similarly, at time 2.07, when I'm down here at the point which is r is approximately 0.756, f is 1.431, the r dt was positive. So that means we're going to the right. We're moving in the positive r direction. The f dt was negative. So we're moving in down, we're moving in the negative vertical direction. So this means we're moving down and to the right at this point. So this gives us this counterclockwise rotation around this curve. So now I've got a direction of motion. So now in this phase plane, I've got information about what the values of r and f are going to be. And I also now have an indication of time by drawing the direction of the motion along that solution curve. Okay, and so to lead into the next topic that we'll be discussing together in class, I want to consider some other vectors that we can draw in the phase plane. So let's consider some of the following points in the phase plane. So let's consider points on the vertical line through r equals 1.25 with various f values. So r equals 1.25, that's going to be a vertical line through this phase plane. And we can consider what would the slopes that I would want to draw at f equals 0, 1, 2, and 3 look like. So we can do the same sort of calculation at 1.250. I can plug this into the differential equation for dr dt and df dt and calculate the corresponding slopes. And so I get dr dt in this case is positive, so I'm moving to the right. The f dt is 0, so that means my vector has no vertical component. The FDR is equal to 0. That means the tangent vector to the curve should be just horizontal. There's no vertical component to it. So the fact that the FDT is 0 tells me that my vector in the phase plane is going to have no vertical component. It's only going to have a horizontal component that's positive, so it's pointing to the right. I can repeat this at the next value for f at 1, plug in 1.25 for r. Now I plug in 1 for f. Again, I get the r dt, which is going to be positive. In this case, it's 2. Again, I get the f dt, which is 0. So again, I'm going to get a tangent vector, which is horizontal. There's going to be no vertical component to that vector again. It's just going to be a horizontal vector, which is pointing to the right. And we can repeat this over and over and over again. And what you should observe is that for any point located on that vertical line in the phase plane on r equals 1.25, the value of df dt is going to be 0. So that tells me all of those vectors are going to have no vertical component. Some of them are pointing to the left. Some of them might be pointing to the right. Some of them might be equilibrium points, but they're all going to have no vertical component. So what that might look like is something like I've drawn down here below. This blue line is the vertical line through 1.25. R is equal to 1.25. 3 of the vectors that we calculated above had positive values for dr dt. So those 3 vectors are pointing to the right. At f equals 3, that vector had a negative value for dr dt. So that's why this one is pointing to the left. Okay, so we'll explore what's kind of special about that, that line r equals 1.25 in some more detail together in class. This is a wrap on that worksheet. Be sure to check out the quiz, and I'll see you all in class. Thanks.